Okay, so we continue to one-sided tests. So previously we have seen an example for the two-sided test for the population variance. Now, sometimes the one-sided test can be useful in some situations. Here we have an example. Suppose we are testing the noise added to the voltage signal in some communication channel. So here we have the pure signal, which is completely, for example, sinusoidal, and there is no noise added to the signal. But in reality, we have a lot of noise and noise resources in electrical devices, for example, or in communication channel. So this is the noise added to the pure signal. So we are afraid that the value of the noise exceeds some tolerated limits. So this is our example. Now the noise is always required to be as minimum as possible. Now suppose in our communication channel the noise tolerated up to have the variance of or sigma square to be 2.5 volt. So if the variance of the noise is 2.5, this is the upper limit to be accepted. Now we are afraid that the noise added to the signal is more than 2.5. So we are checking the value of the variance for the noise. If it is maintained maximum by 2.5 for the variance, or this was violated at some moments at some specific times. So now suppose this is our example. So we have taken a random sample of 30 points or 30 samples in the communication signal or in the communication channel. So we have taken 30 random readings or measurement from our population. Here our population is the signal transmitted or in the communication channel, and we have taken a sample of 30 points or 30 readings. Also, we have computed the sample variance using the same equations as we have seen before. We have computed the sample variance to be 3.5. So firstly, we formulate our hypothesis. The first or initial assumption, we have the variance of our signal to be 2.5, and we are afraid that the noise has caused the variance to be larger than 2.5. So our alternative hypothesis is sigma square is larger than 2.5. Now, because we have larger than, we have one-sided test. Also, we are going to use the 95% confidence level. So the same as before, we are going to compute the chi-naught square, which is our test statistic. Here we have n-1, which is degrees of freedom. We have 30, so 30 minus 1 is 29. We have the sample variance to be 3.8 after we have calculated this. We have the hypothesized variance or the hypothesized values of our population to be 2.5, which we have taken from the null hypothesis. So we compute the chi-naught square. We found that it equals to 44.08. So approximately the chi-naught square is 44. Okay, so now this is our chi-square curve or distribution. Now firstly, because we have a single or one-sided test, we have alpha in one side. Here we have alpha in one side to the right side because we have greater than in the alternative hypothesis. We don't divide alpha as alpha over 2 to the right and alpha over 2 to the left because we don't have two-sided test. We have only one-sided test, so alpha is completely here to the right of a specific point. So this value is the critical point that we should compute from the chi-square table. We have chi-square for a specific value of alpha and v, where alpha is 5% because we have taken the confidence level at 95%, so alpha here is 5%. This is the rejection area, and we have the acceptance area, which is 95%, which is the white area under the curve. So now from the chi-square table, we have found the chi-square for 5% and 29 for the degrees of freedom to be 42.56. Also, we have computed the chi-naught square to be about 44. We notice that the 44 or chi-naught square falls in the rejection area. So our conclusion will be to reject the null hypothesis because chi-naught square has fallen in the rejection area. So we reject the null if chi-naught square is larger than the critical value. We have computed the chi-naught square. We have computed the critical value for the chi-square when the area to the right of this point is 5% and the degrees of freedom is 25. We found that the chi-naught square falls in the rejection area, which is shaded in blue. So this is the rejection area. So our conclusion is to reject the null hypothesis. So now our solution was to reject the null hypothesis. So what does that mean? This means that the noise values are more than the tolerated level. So we have noise variance larger than 2.5. So here we have a problem in this communication channel or in the equipment or devices to transmit this signal. Therefore, we should have a new method or filtering is required to eliminate the excess of noise. So this is a quick summary about the hypothesis and testing for the population variance. We always have the null hypothesis as variance or sigma square equals specific value. For the alternative hypothesis, we either have the two-sided test or we can have one-sided as larger than or one-sided test for less than. The test statistic is always the same in all cases. We have the chi-naught square to be the degrees of freedom or n-1 multiplied by the sample variance divided by the hypothesized variance of the population. So in case of two-sided, we are going to reject the null hypothesis if chi-naught square is larger than the critical value to the right or less than the critical value to the left, in case we have two-sided. So here we have alpha over 2 to the right, and here we have alpha over 2 to the left side. But in case we don't have this relation or chi-naught square falls into acceptance region, we are going to fail to reject the null. Also, if the alternative hypothesis is larger than, we are going to reject the null hypothesis if chi-naught square falls in the rejection area, which means chi-naught square is larger than the critical value. In case we have less than in the alternative hypothesis, we are going to reject the null hypothesis if chi-naught square is to the left of the critical value or less than the critical value. So here in the one-sided test, we have the completely alpha as the area under the curve, and here also alpha. But in two-sided, we have alpha over 2 and alpha over 2. So this is the summary of testing of a population variance based on the chi-square distribution.